T3 Day 8 of Calculus. Today we're going to discuss the fundamental theorem of calculus. Super exciting. So first, let's talk about velocity again. So we have a velocity graph. It's nice and straight, fantastic. And we're going to write an integral expression that represents the change in distance and evaluate it for the first second. The first second, and then the first 2 seconds. So what is this integral expression going to be? Remember, it's the change in distance. So it's going to be the integral from 0 to 1 of v of t dt. And what does that represent? That represents the area under the, quote, curve. In this case, it's a straight line, but we can call it a curve, from 0 to 1. So in this case, it's this area right there. So that's going to be the area of a triangle, and in this case, it's going to be 1/2. The base width is 1, and the height is 5. So 1/2 base times height is 5/2. So if this is feet per second and seconds right here, feet per second and second, this means that this unit is going to be feet. So the net change, the change in distance, will be 5/2 feet. What about the first 2 seconds? Well, it's similar. It's 0 to 2 of v of t dt, and that's going to be 1/2. The base in this case is going to go all the way to 2. So the base in this case is 2, and the height in this case is all the way up to 10. So that's going to be 20/2, which is 10. So the change in position is 10 feet. What about the first 3? Well, you're sensing a pattern here. We're going all the way up to 3 here. So we go all the way up to here. So it's 0 to 3, 1, so not 1/2. We got to actually write v of t dt. So it's v of t dt. It's going to be 1/2 base times, and what's the height this time? 15. These are nicely lined up, aren't they? So we have 45/2 feet. What about the last one? I'll go to the blue highlighter here. So it goes all the way up to here. So it's going to be 0 to 4 of vt dt. And in this case, it's going to be 1/2 base. In this case is 4 times the height is 20 in this case. So that's going to be 80/2, which is 40 feet. So remember, this is the change in distance. So we don't actually know where the particle is. We just know that wherever it started at time equals 0, the net change in these instances will be like this, those numbers. So suppose that at time equals 0 now, suppose at time equals 0, the person's distance is 5 feet from home. So the person is starting 5 feet from home. Write an integral expression that represents where she is after 1 second. So what that means is the initial position, remember it's s of 0 plus the net change. This is s of 0 plus the net change. So it's the starting position plus the net change from 0 to 1. We know that this right here is 5. We know it's 5. That's 5 right there. The initial position. And we know that this right here is, from the original part I, is 5/2. So in this case, what's the position, the actual position where this person is after 1 second? Well, it's going to be 5 feet from home plus a net change of 5/2. So what is that going to be? Well, you can write it as 10/2 plus 5/2 is 15/2 feet from home. So now we know the exact place this person is, but we needed to know this. So what about 2 seconds? Well, it's going to be the initial position, which is still 5, but I'm going to write the general equation first, 0 to 2 of vt dt. Remember, this is the change in position after 2 seconds, and this is the initial position. The initial position is 5, but we now know from above that from 0 to 2, the net change is 10 feet. So what do we end up here? 5 plus 10 is 15 feet from home. So you can continue with the same logic and do I and 4, well, 3 and 4. So you write out those two integral expressions, and in this case you end up with 5 plus 45/2, that 45/2 is from above, and 5 plus 40 over, not 40, it says 5 plus 40 right there. So you end up with this many feet from home, and this many feet from home. So the key though is you need the initial, like where you need a position of the person, and then the displacement from that time. You'll notice that the key thing is we're going from S0, which is S0, and then 0 to 3. Notice how all these, there's a link right there and a link right there. Now in this question, it's asking to sketch a graph of s of t. This is the position, So we know that at time equals 0, where is this person? So we need to just write out the points. We know that when s is 0, so this is s of 0, it told us above that it's 5. And we know that the position at 1, what was it? we can write out these values here. We know the position at 1 was 15 over 2. These are all in feet. And we know that S of 2, the position at time equal 2, was 15. And what was it at S3? S3 was this sum, which comes out to 55 over 2 feet, so 55 over 2. And S4, the position at 4 seconds, was 45 feet. I can write feet pretty well there. I can almost write it really well. So now we just graph those points. So S of 0 is 5 right there. So S of 1 is 7.5. It's right about there. Then S of 2 is 15 right there. And then S of 3 is 55 over 2, which is 25, 27.5. 27.5 is like right there. And S of 4 is 45. 45 is right there. So what do we have here? This is a distance away from home right here. So this is distance away from home. So we have time, we have position right here. Time and position. Let's talk about increasing, decreasing, and concavity. So it looks like this entire thing is increasing the entire time. It's increasing, and it's, what's the concavity look like? Well, it looks like it's a smiley face, so it's concave up the entire time. So what have we done here? We've gone from velocity back to the distance function, but the key was we needed an initial position. We needed a position because change in distance doesn't tell us anything about where we are right now. I could just tell you, I just ran 10 feet. Where am I? That tells you nothing about where I am right now. You need a starting position, or at least one place on the track. So the way you can say this is the place you are right now, S of B, the position right now, is where you started. So this is your starting position plus the change in position, right here, the change in position. So you can rearrange this a little bit, and all that's happening here is we're subtracting the S of A and putting it on the other side. So what this says is where you are right now, you subtract from it where you were, so like where you started, equals the net change. That kind of makes sense. That's the net change. Net change. So then when we just reverse it, and we like to say this right here. This is the thing we like to say right here. The change in velocity is where you end up minus where you started, which kind of makes sense. The change in the amount of velocity change. So your net change in position is equal to where you ended up minus where you started. Now the problem though is that you don't really know what S is. Like you don't know what the function for S is, and I'm about to give you that. So here it is, the big fundamental theorem of calculus right here. This is what you really should memorize. So this right here represents the area under the curve of lowercase f from A to B, right there, lowercase f of x. So that could be velocity. That's going to be equal to capital F of B minus capital F of A. Notice the capital difference, where this right here, the capital F of B, is called the antiderivative of f of x, meaning the derivative of capital F of x is equal to f of x. The derivative of capital F is equal to lowercase f of x. So what does this mean? So I'm going to do a bonus example here. I could ask you, what is the integral from 0 to 2 of x squared dx? So this isn't a straight line, so you can't really use adding up triangles to find this exactly. You could estimate it using Riemann sums, but let's use the fundamental theorem of calculus. So in this case, our A value is the 0 and our B value is 2. So what this is telling us is this is equal to capital F of 2 minus capital F of 0. And it tells us that if this is f of x right there, this right here, we need to find out the derivative of what is x squared. The derivative of what is x squared. So the derivative of what is x squared? It's going to be x to the something power. Well, we know when we take the derivative, it goes down 1, so it's going to be x cubed. But if I just took the derivative of x cubed, I'd end up with 3x squared. Is there a 3 out front? There isn't. So we need to take care of that. So what we're going to do is put a 1/3 out front. Let's check this. What happens when you take the derivative? What is d dx of 1/3 x cubed? Well, that's 1/3. The 3 drops to the front. You reduce the power by 1, but the 3 and the 1/3 cancel, leaving with x squared. Oh, there it is. So what does this mean the answer is? It's f. In this case, it's going to be x cubed when x is 2 minus x cubed when x is 0. So the way you write this is you'd write x cubed when x is 2 minus x cubed when x is 0, like this. Oh, but wait, we forgot the 1/3 right there. So you plug in the 1/3 out front of each of these. You can just pull it out like that, and what do you end up with? you end up with 1/3 of 2 cubed, which is 8. So the area under that curve is actually 8/3. The key is that you need to find out what is the antiderivative of x squared. So in that case, this is the lowercase f of x, and in the capital F of x is 1/3 x cubed. You are going to undo lots of the derivative rules that we just did. We're going to undo lots of the derivative rules, and it just takes practice.